Welcome to Fundamentals of Artificial Intelligence. Today we will look at searching AND/OR graphs. AND/OR graphs are structures that are used for representation of solution of problems that can be decomposed into smaller problems. Solution of these smaller problems has to be accomplished in order to complete the solution of the original problem. We have looked at AND/OR graphs while we were discussing production systems, particularly decomposable production systems, which allowed a problem to be broken up into smaller problems, and solution to these smaller problems led to the solution of the original problem. Let us look at what we mean by an AND/OR graph in more detail now. Let us say we have a problem S that could be solved by either going to A or by B and C together. It is interesting to note there that several arcs may emerge from a single node, indicating a variety of ways in which the original problem might be solved. In this example here, S could be solved if I have solved A, or it could be solved by solving B and C, both of them. When it is solved by solving B and C both, we tend to name it as an AND arc, and the AND arc point to a number of successor nodes, all of which must be solved in order for the arc to point to a solution. Here in the example that we were looking at, B and C both needs to be solved to solve S. AND arcs are indicated with a line connecting all the components. So, for B and C, which are AND arcs, we will try to use this arc here to indicate it that it is an AND arc. Before we move on to understanding AND/OR graphs, let us review what we mean by hypergraphs. So, hypergraphs are where the arcs connecting pairs of nodes are referred to as hyperarcs. They connect a parent node with a set of successor nodes. These hyperarcs are called connectors. So, coming back to the example that we were discussing, here B and C together has to be solved to solve S. So, the link between these two is referred to as a 2 connector. So, each K connector actually is a directed arc from a parent node to a set of successor nodes. Here between BC, which is to be both solved for S to be solved, we have an AND connector. If all of the connectors are actually 1 connectors, then we have the spatial case of an ordinary graph. So, hypergraphs are used to define AND/OR graphs. Here is an example of an AND/OR graph. For every K connector with K greater than 1, we could see that we are denoting with a curved line. So, here is a 2 connector, here is again a 2 connector, here is a 2 connector. Node S here has a 1 connector that goes to successor A and has a 2 connector that goes to D and E. The decomposable production systems that I was referring to actually defines an implicit AND/OR graph, and the initial database corresponds to the start node S. Kindly recall what we did in our production systems lecture. We looked at a decomposable production system for rewriting rules. So, we had an initial database CBZ, which could be broken up into 3 databases C, B and Z. Now, each of these could be applied rewriting rules, like C could be rewritten as DL or C could be rewritten as BM, So, here we have an OR node, but when we had splitted the main problem into 3 component problems C, B and Z, we have an AND node. So, decomposable production systems defines an implicit AND OR graph. One difference that you must have noticed by this time is that when we are talking of decomposable production systems, the AND and OR nodes are at alternate levels, whereas in the graphs that we have introduced today, both the AND arc and the OR arc are at the same node, but there is not much of a difference. We can move from one to the other. So, let us look at this with an example. Here is our graph S with an A and a 2 connector leading to B and C. We can replace this with the graph on the right, where we maintain the fact that there are 2 possibilities of solution for S, one going to A and the other going to B and C together. So, for that we introduce an auxiliary node D, and D will be solved if we could solve B and C. So, we can transform the graph on the left to one on the right, but of course, we need to keep track of the cost of the edges. Having introduced the concept of an AND OR graph, let us now look at what do we mean by solution of an AND OR graph. Solution of an AND OR graph is analogous to a path in an ordinary graph. So, let us look at this example AND OR graph. Here, if we are looking for a solution from node S to the set of solution nodes, which are G and H, we want to explore starting at S and select a connector to take us to the successor nodes. Thereafter, from each successor node, we again select an outgoing connector, so on and so forth. Eventually, every successor needs to be an element of the set N, which is the set of goal nodes. So, let us take S first, and then we will take the one connector. We come to the node A. The node A, we need to realize, has 2 paths, one going to B and one going to C, but then these are OR, and therefore, we could pick up one of them. So, we proceed to B. Now, it is interesting. If you focus your attention to the node B, you would realize that B has a 2 connector leading to nodes F and node D. What this means is that in order to solve B, I need to solve F as well as solve D. So, next I follow that 2 connector, arrive at F, arrive at D and look for solution to F and D. The next node to be expanded is D, and now again we see that D is a 2 connector leading us to G and H. So, we solve D by going to G and H, and now we solve F, which is a 2 connector again leading us to F and H one more time. So, after we have traversed from S through A to B via FD, we have arrived at GH, which is the set that we want to have arrived at from N. So, this is the solution graph. Now, if we focus on each of the nodes of the solution graph, it is interesting to note that once G and H are solved, I know that D would be solved, because D is an AND node between G and H. Once I have G and H solved, I can also see that F that has a 2 connector leading to G and H, I can have that as solved, and then once F and D are solved, I have B marked as a solved. Thereafter A could be marked as solved, and thereafter S could be marked as solved, because for solving S all I need is solving A. This is the solution subgraph for the AND OR graph that we started with. Let us now see if there are more than one solution to this graph. Recall that we had started by following the one connector from S leading to A. Instead of that, if we follow the 2 connector, that is, we move this way leading from S, then we would have to solve first by moving to E and then moving to D, because they are on an AND arc. Once we have solved D and E, we can look at E, which has a 1 connector to D, so we can mark that. Therefore, we have got the next node on E, which is D. At D, we realize we have a 2 connector leading to G and H. So, we will mark that, and we have arrived at the solution set. So, this is an alternate solution subgraph for the AND OR graph that we are illustrating here. We can now think of going back and looking at if we have solved each of the nodes on our traversal. So, as before, you would see that we have solved G and H. So, that means we have solved D, which is an AND of G and H. And now, if we see S, before we can mark S to be solved, we need to realize that we need to mark E. We have one connector between D and E, and D is solved. Therefore, we could mark E as solved. Once we mark E as solved, we can now mark S as solved. So, this is the solution subgraph of the AND OR graph. So, as we can see from this example, for a given AND OR graph as simple as the one we have shown here, we have highlighted 2 solution graphs. The idea is, how do we get to the most optimal solution graph? For that, we need to search through the AND OR graph, and we need an algorithm, something like the best first search. But then, as we will see in the next few slides, the best first search may not be tuned to do a searching on the AND OR graph. This is because of its inability to handle the N arcs appropriately. So, we are looking for some algorithm which does something like the best first search, but should be able to handle the N arcs appropriately. This is what we will try to understand in this part of the lecture. And another thing is the algorithm that should find a path from the start node to the set of node representing the solution states may be required to reach more than one solution state. Now, we should realize that this is precisely because each arm of an AND arc must lead to a solution node, and this is something we must take care of when we are writing this algorithm, that after we realize that we have expanded a node and we have reached the solution nodes, we should go back and see if the parent can be marked solved. This is only possible if all the successor nodes of a K connector arising from a given node has been solved. Then only I can mark that particular node N as solved, and that we need to ensure. So, we will look at this, but before that we will look at what is that makes the breadth first algorithm inadequate to deal with searching and or graphs? So, here is an example to start with. I have a node S and I have an arc coming out of this to A, and an alternate solution involves B and C together. So, this portion of the graph here shows that I have a 2 connector. In order to solve S, I would need to solve both B and C. Now, what we have here with the nodes marked is a heuristic value. This is something like the heuristic value that we have looked at when we were doing problem solving as search and trying to look at informed search. Only difference here is that these heuristic values contain the promise of the node and gives us a measure of how good it is to take it to the solution. We do not store here the cost of coming to this present node. So, if you assume that each edge costs 1 unit and I was just doing breadth first search, then my algorithm would be choosing node B for expansion. This is because node B has the minimum cost to the goal. But then is it the best path? If you look at the cost of the path, you will see that B is part of an AND arc. So, if we choose B, we must also use C. So, involving B would mean that I would be expanding 4 units at B, 5 units at C, and because this is a 2 connector, I would be spending 2 units there. So, I would be having an estimate of 11 on this path. Whereas, the other path from S to A, all I spend is 5 units that takes me to the solution from A and 1 unit because of the edge. So, I have 5 plus 1 and which is 6, and this is definitely better. So, actually I must traverse this path. So, this is something which is not possible from just looking at the heuristic value of that particular node. Let us try to understand this with one more depth of search. Let us say now I expand node A and arrive at D and E. Node B is expanded to, let us say, F, G, C is expanded to H and I. Now, if you look at the edges, then possibly one involving B, F, G here has the lowest cost, because this would be 2 plus 4 plus 2, which is 8. This would be 5 plus 3, 8 plus 2, 10, whereas this one here would be 7 plus 5, 12 plus 2, 14. So, possibly this is the best, but the question is it true? If you look at more closely, you will realize that even if this path has a cost which is lowest, but then involving this path in this solution would also mean that I have to involve C, and therefore, this cost would be added. Under this present scenario, the best would be to go along this path and expand D and E further. So, we had looked at these inadequacies of the best first algorithm, its inability to handle the AND arcs, and therefore, would look at a more specialized version of searching and or graphs.